So, students, our today's class is vibrating diatomic molecule as a harmonic oscillator. Okay. So, before this, let me tell you that in our previous class we have learned about the molecule that can be considered like this, which have rotation, something like this, right, or like this. And this kind of molecule can have an example something like this, CH3, and then sorry, it's not this one. Okay, so yeah, CHH CHS, right? So this kind of molecule can rotate something like that, right? Or I can write something like this, CH3 CH3, right? So they will rotate like this, or they can rotate like that, right? So in this class what we going to learn is not the rotation or like this one, but the vibration. So like this, or they come nearby, or they go far, right? So these are vibration. Okay, so this is the vibration, right? Vibration, and this is rotation, right? So this one you can say rotation. For vibration it should have this kind of movement. Okay? Now for that, what we need to assume is a molecule, diatomic molecule, right? We assume a diatomic molecule, right? Which is, suppose at the beginning it is here, the distance is very less. So here is the C point, is the center of mass, right? So this is a molecule, so this is M1 and this is M2, right? So after some time, suppose they move away certain distance, right? Okay, suppose this distance we call R1 dash, this is we call R2 dash. Okay, now they have a new distance, as a whole their distance is suppose R0. Okay, so this is the position C, center of mass position, and this is M1's distance from center of mass C, this is M2's distance from center of mass C. So then what will be the restoring force? Okay, we know restoring force is, suppose for example in your practical exam, you know, if there is a spring, okay, so if you pull it, there will be restoring force in opposite direction, right? And this restoring force actually will start from the mean position. If it is the mean position, now you pull it, it will come here, then from here this restoring force will start. Okay, in here also what will be the restoring force now? Okay, from this position this distance is R1, so the restoring force, because the tendency of this atom or this atom with other ligand is to come to this position, right? So this is this point, something like that. And for this one you can assume it something like this, right? So something like this you can assume, right? Or suppose what let's, yeah, C position, something like this. Both of them you put, but the restoring force will act from here, sorry, not from here, from here. Restoring force will act from here, right? So in this case the restoring force on M1 is M, so F1 is equal to M1A, right? Suppose A1, F equal to MA, so M1A will be equal to D, how much distance you pull will give you the restoring force, and D square R1 dash by dt square, and on M2 is F2 equal to M2 d square R2 dash by dt square, right? This is the restoring force. But now suppose we have another scenario, right? So the scenario is, suppose now this is the C position, right? So this is M2, this is M1, and the distance between them is suppose R0. So we know if this is R dash R1 dash, this is R2 dash, then the restoring force will be M1 d square R1 dash M2 d square R2 dash by dt square, right? But now suppose we pull it more, right? This is here, this is sorry, this is M1, this is M1, this is M2, right? So this distance is suppose R1, this distance is suppose R2. We know this distance R1 dash and this distance R2 dash, and as a whole this distance is R, right? So now therefore so let's start again in another page. The next page we will know. Let me draw it again for a more clear picture. See, M1, M2, R1 dash, R2 dash, and as well this is R0. This is the new position. C, R1, R2, and as well this was R. This is M1, this is M2. Okay. Therefore, now the new restoring force. Now the new restoring force on M1 will be this distance, will be equal to M1 d square R1 divided by dt square, and on M2 is and on M2 is sorry, M1, this one will be equal to F1 M2 d square R2 by dt square F2, right? Yes. So these are the restoring forces. Oh, sorry. So you cannot see it. Okay, let me write here. So again, so the new restoring force on M1 is F1 equal to M1 d square R1 by dt square, and on M2 is F2 equal to M2 d square R2 by dt square, right? Again, the relative distance moved by these two masses now should be equal to, so what will be the relative distance? So this distance will be here and here, right? And how to obtain this one? We can obtain by divide minus R minus R naught, right? So again the relative net distance moved by the two masses are R minus R naught for both the two masses, right? For both the two masses. Why? Because if you consider as a spring, as I have explained before, right? So, right? So the relative distance will be from here, if it's moved from there, from here it's moved from there to here, then the relative distance will be this one minus this one, right? But the restoring force will always act from here, this point. Okay, so therefore the simple harmonic motion equations for both the masses are, number one will be m1 d square r1 by dt square equal to minus k r minus r naught, which is coming from the equation m d square x by dt square equal to minus kx. It's like the pendulum equation, you all know, right? And for mass 2 is m2 d square r2 by dt square is equal to minus k. It will also be same because the restoring forces are from here, right? D square r by dt square for this one, or from, if you see, from this one, right? But the relative distance is for as a whole, okay? And it's the same for both the masses, okay? Now let's go to next page.